Dear students, so today it's our first offline lecture. Um, I will try my best to explain the lecture as if we are face to face. Hopefully it would work out. I will talk in first of all about the example that we have skipped last time. So as you can see, we are going to estimate the concentration of carbon dioxide originally present in water. So for that, we need, as you can see here, the first dissociation of carbonic acid, because carbon dioxide, once it's dissolved in water, it would form carbonic acid, and carbonic acid undergoes two dissociations, the first dissociation and the second dissociation. What we need is the two equilibrium constants. For that, we have these two equations that are based on the temperature. So you have the steps here, but in order to understand the steps in a better way, we can go to this example. As you can see here, we need to calculate the concentration of carbon dioxide having a pH, having a water with the water having a pH of 7.65. The water has an alkalinity value of 310 milligram per liter, and the temperature is 25 degrees. So the first step, we need to determine the H plus. Since we have the pH, we can calculate the H plus concentration by the well-known formula, which is H plus concentration is equal to 10 to minus the pH value. So if we take 10 to minus 7.65, this equals to 2.24 10 to minus 8 moles per liter. Now we need the concentration of the alkalinity components, which are normally carbonate and bicarbonate, which means CO3 minus and HCO3, CO3 minus 2 and HCO3 minus. However, since the pH is 7.65, it means that the predominant element is the bicarbonate. And that's why you can see here in this step, the 310 milligrams are considered as bicarbonate only. And this is due to the pH, as I said. At this pH, basically we have no CO3 minus 2 available. However, another problem is that this alkalinity is expressed in terms of milligram per liter SCaCO3, and of course this cannot, as units, cannot be used in the equilibrium equations. So it has to be converted into moles per liter. In order to do so, first of all, we have this step. Okay, the first two terms between parentheses here. So if we multiply by the equivalent weight of our HCO3 minus, which is 61 milligram per equivalent, and we divide by 50 milligram per milli equivalent, okay, this would give you the concentration of HCO3 minus in milligram per liter as HCO3 minus. So this is also not enough because we need it in moles per liter. So after this first step, we have here to divide by the molecular weight of the bicarbonate, which is 61 gram per mole. Of course, you have here the milligram per gram, and this is just to get consistent units. So it's a conversion factor. So finally, we will get a value of 6.2 10 to minus 3 moles per liter for the bicarbonate concentration. And then afterwards, simply, we need to substitute these values into the dissociation equation. So the H plus value is available now, the bicarbonate is available, and the Ka1 can be easily determined because we have the temperature based on the equations I showed you in the previous slides. So you will get a carbonic acid concentration of 3.11 10 to minus 4 moles per liter. However, this example asks for the concentration of carbon dioxide. But since we know that the carbon dioxide ratio to carbonic acid, like once the carbon dioxide is dissolved in water, to give carbonic acid, the ratio is 1:1. So basically, we can assume that the carbonic acid concentration is the same as the carbon dioxide concentration. We can stop here with the moles per liter, but however, if you want to convert this concentration into milligram per liter as CO2, sorry, we can proceed simply by multiplying the concentrations in moles per liter. Of course, this is quite obvious, by the molecular weight of carbon dioxide to get 13.7 milligram per liter as carbon dioxide. We can even proceed further to get the concentration in milligram per liter, this time as CaCO3. So we need to take this concentration up to here, multiply it by the equivalent weight of CaCO3, divided by the equivalent weight of carbon dioxide. Now the question, how did we get this 22? Now we know that the carbon dioxide molecular weight, first of all, the equivalent weight of carbon dioxide, it's the molecular weight of carbon dioxide divided by the charge. So the molecular weight of carbon dioxide is 44. I have to divide this by the charge, but the charge of carbon dioxide is not quite clear which charge I have to use. So since we know that the carbon dioxide to carbonic acid ratio is 1:1, so basically the origin of carbon dioxide is carbonic acid, we can break down the carbonic acid into two parts. So we will have for the anions -2, for the cations, the 2H pluses here +2. So we take just the absolute value of the charge, which is 2. So we divide the 44 by the charge, which is 2, coming from the charge of the carbonic acid. We will get this 22 here, okay? And then you will have the concentration in milligram per liter as CaCO3. So what I have explained, it's here, it's mentioned in the last line. Okay, this is an example that we have done last time, so I will skip it. Just one comment that I need to stress on. It is this discussion we had last time for the 30 and 10 milligram per liter. Just to remind you about this, we said we have two conditions or two requirements. Either we say we're going to remove by softening all the calcium, and the remaining is 40 milligram per liter as magnesium. The whole quantity is 40 milligram per liter as CaCO3. Please keep this in mind. It's as CaCO3, magnesium. Or if we have both remaining in water, we can split them, okay, to have a total of calcium and magnesium, as you can see, of 40 milligram per liter. So last time we had the discussion about the 30 and the 10 milligram per liter as CaCO3. Now this 30, actually, the solubility, the practical solubility of calcium as ion in milligram per liter as ion, as calcium, it goes from 10, as I told you last time, it goes from 10 up to 20. It depends with which anion is the calcium combined with. So, but in all cases, it goes from 10 milligram per liter as calcium to 20 milligram per liter as calcium. If you convert this and take an average, it would be like 30 milligram per liter as CaCO3. That's why we had a confusion last time. So it is between 10 and 20 milligram per liter as calcium, but when we convert it into milligram per liter as CaCO3, it is 30 milligram per liter as CaCO3 and 10 milligram per liter as CaCO3 coming from magnesium. So this is for calcium, this is for magnesium, and we have no problem here. So it is 30, yes, for calcium, but however, it is 30 milligram per liter as CaCO3 and not as calcium. And here it is 10 milligram per liter as magnesium. Then you can wonder why we have this 3:1 ratio. Why 30 for calcium and 10 for magnesium? Why, when the magnesium is left alone in water, we take the final concentration as 40 milligram per liter. However, when it is remaining co-currently with calcium, it is 30 to 10. Okay, This was decided based on the fact that the calcium is a predominant element. Usually the calcium is present in water with higher concentrations than magnesium. And also back again, taking an average, okay, it is maybe 3 to 1. So they said, okay, if we have both of them present simultaneously at the same time they are there in water, so we can say, okay, this total 40, 30 is for calcium because it's the predominant, and 10 as, of course, back again, milligram per liter SeSO3, 10 for magnesium. Okay, so it is here, this is completely correct. Now, let's move to a new type of softening. It is the splat treatment. And the splat treatment concept actually relies on the fact that we have to split the stream of raw water into 2 parts. Um, so we have to treat a portion of the raw water and to leave the other portion untreated. We have 2 purposes for that, actually. The first purpose is to reduce the amount of chemicals that should be added to water, for softening. The other point is to reach the final requirement, which is 40 milligram per liter SeACO3 without touching the magnesium. So if we can just treat with removing the calcium and having a final concentration of magnesium of 40 milligram per liter, as we have seen in the scenarios presented in the previous lectures, actually the magnesium, it should not be removed. And also there is a reason behind that. It's that the magnesium removal is expensive. That's why we would prefer to remove calcium rather than magnesium. Okay, so this is the concept, this is the theory behind the splat treatment. Now we have to decide what is the fraction of the water that should be treated and what is the fraction of the water that should be left untreated. So we have this X. The X means it's the fraction of the water that should be remained untreated. Okay, so for example, if I have an X here of 40, it means I have to treat 60% and to leave 40% untreated. Okay, how can we determine this X? So this X is fully based on the magnesium concentration, okay? Because we know that in splat treatment, we will be basically removing the calcium. The magnesium will stay untouched. And that's why we have to keep an eye to fulfill the requirement of magnesium, which is uncontrolled with the splat treatment. And that's why we rely on the magnesium concentrations. So the equation here says that X equals to mg final minus mgi, mg over mgr minus mgi. Mg final, it means this is the final concentration of magnesium we can get after mixing, after treating this the stream and then mixing it with the untreated stream. Let me show you the flow chart. So here at this point, okay, after mixing, after the junction point, this is the Mg final. I have another flow chart which is which is clearer than the first one. So as you can see here, for example, I have the raw water, so this is the MgR, okay, which means this is the initial magnesium, okay, and then we go, let's call it Mg raw, and then we go, okay, we split here the stream. This is untreated, it goes with no treatment, and this is the treated, okay. After treatment and before mixing at this level, this is what we get here as a magnesium concentration is called MgI, okay. Now after mixing the MgI stream with the untreated stream, and of course in the untreated it means the concentration is Mg raw because this stream is kept untouched. So I have the MgR here mixed with the MgI, which is the concentration after the softening process, which is included in the splat treatment. We mix here what we can get. Okay, here Okay, it's mg final. If we go for further treatment, I will discuss this, another treatment, okay, the mg final will be here at the end, okay? But for example, here at this stage, as you can see, where is the cursor? This is mgr. Here, before mixing, it is mgi. Here I have, because this is untreated, mgr. After mixing the untreated with the treated, okay, having a concentration here of of mgi, you will get here an mg final. Okay. And using this equation, I can get the x. As I told you, if we, for example, let's say that we got a value of 40%, it means 40% of the water has to be kept untreated, and the other 60% has to be treated by split treatment. Okay, so for example, the 60% goes here, okay, and the 40% goes here, and then they are mixed at this level, and then here. So sometimes if we check the requirements, of course the magnesium will definitely fulfill the requirements, because the whole process, okay, has been based on the magnesium. However, sometimes due to the very high concentration, okay, and even with blending, okay, we will get a high hardness at the final stream here after mixing, which means that, okay, the split treatment somehow was unsuccessful, because the water quality in the final stream after mixing the treated part with the untreated part does not fulfill the requirement. In this case, we go to the second flow chart, okay, this one. So you have here the split treatment. If it's still the water here is not meeting, or is not meeting the standards, or is not fulfilling the requirements, which are the practical limits for magnesium and the practical limits for the total hardness, in this case we have to go for a second stage of softening, lime soda ash, which is a classical one. What do we mean by a classical one? It means it can be selective calcium removal or excess lime removal, which means selective calcium removal. I will only remove the calcium if the problem is with the calcium. If the problem is with calcium and magnesium, we have to remove both. And this method is called excess lime softening. Okay, and that's why we need two stages. Of course, sometimes if everything is going well, okay, we can do it by one stage, which is the split treatment. Anyway, we will take an example just to clarify how can we design a split treatment method. Okay, as you have noticed, in both cases, we need what we call recarbonation directly after the softening stage. If it was carried out uh, in one step, also, as you can see here, we need a recarbonation, okay, if it has been carried out with two stages. So, in all cases, after softening, we need a recarbonation. Okay, we will talk about recarbonation. This is just to simplify things for you before proceeding to recarbonation. This is an equation that you can use, okay, and it simplifies for you the calculation of X. Usually we take the final concentration of magnesium, MgF, as 40, which means this is, okay, the maximum concentration of magnesium that we can accept after blending. Okay, let's put 40 here. What is the minimum solubility of magnesium that we can reach? Is 10. This is the minimum at the best case scenario. So if we say 40 minus 10, this will give 30. MGR, of course, this depends on the raw wastewater, so we have to analyze the wastewater in order to get the value here. And back again, the MGI is 10. So you can use this equation to determine the X with only one unknown, which is the MGR. Okay? Of course, sometimes we can change like the MGI here, but if unless it's stated otherwise, you can use this equation. If it's not like the conditions are not changed, you can directly use this equation. by only inserting the value of mgr, and then you can get the X. Okay, now let's go back to the recarbonation. Why do we need recarbonation? Because in all cases, whether we are uh, using the split treatment, or we are using the selective calcium removal for softening, or we are using the X-slime process, okay, for all softening scenarios, the pH after the softening is higher than the pH of saturation. If we refer back to the concept we talked about at the beginning of this chapter, when the pH is exceeding the saturation value, it means that your water is unstable, which means we risk to have a further precipitation of calcium carbonate even after finishing the softening, and this would take place in the pipes. So maybe we will face a clogging problem. So to stop the precipitation, as we said, the main solution to bring back the pH after softening from the high pH to the saturation pH, which is a stabilization, you can call the recarbonation a stabilization step. We have to bring it back to the saturation. Okay, if we have a high pH and we need to lower it to the saturation, we need to add a source of acidity, exactly a stabilization step. So usually, as we said, a natural acidity source, it's the carbon dioxide, because when it's dissolved in water, it would give the carbonic acid. So as you can see, let's go stepwise. So for example, recarbonation after selective calcium removal. Usually after this, you will get, after a softening with selective calcium removal, you will get a pH from 10 to 10.6, and you have to bring it back to 8.5 to 9, which is the saturation. Okay, in order to do so, we add carbon dioxide, and let's see what happens. Once the calcium carbonate, which is dissolved in water, reacts with carbon dioxide, all the carbonate would be converted to bicarbonate. So this is a reaction which is completely going in the opposite way as we did in softening. In softening, we convert HCO3 minus to CO3 minus 2. In this case, when we are adding the carbon dioxide, it's the other way around. We are converting the CO3 minus 2 to HCO3 minus. So this, the HCO3 minus, would not react with calcium to form CaCO3. In this way, we stop the deposition or precipitation of calcium carbonate, and we can overcome the problem of clogging. Now, what if we have X-slime process? Okay, so it means that we are basically removing calcium and magnesium at the same time. In this case, we have two steps. First of all, just for you to know, usually when we finish this softening step, the pH is around 11, as you can see here. We have two steps. First of all, we bring the pH back to 10 to 10.5, and then from 10 to 10.5 to the saturation, which is between 8.4 to 8.6. In the first step, as you can see in the reactions, we add carbon dioxide to calcium. It would precipitate as CaCO3. When we add carbon dioxide to magnesium, it would form MgCO3. And directly, we need to add additional amount of carbon dioxide to capture this CaCO3. As you can see, it's here. It would react with carbon dioxide, and directly we're converting the CO3 minus 2, which is inside the calcium carbonate, to HCO3 minus. And in this way, we can stop completely the precipitation. Okay, same thing applies to MgCO3. If we add carbon dioxide, this carbonate would disappear because it will be converted to bicarbonate. So recarbonation, as you can see, it is just a stabilization step after softening, okay, in order to bring the pH back to the saturation, because we have, like in softening, we, as you remember, we added lime in order to raise, to how to say, to take out all the carbon dioxide and to raise the pH. because the precipitation of calcium carbonate would not take a place at low pH. So in softening, we raise the pH. Once the softening is done and it's over, we have to bring back the pH to saturation, to the pH of saturation, which is called recarbonation. That's why, as you can see here, all the time we have softening, afterward recarbonation. Same here, softening, afterward recarbonation. Of course, we need sedimentation exactly after softening because we're waiting for the CaCO3 and Mg hydroxide to precipitate. I mean, in split, of course, in split, we're talking about calcium. So CaCO3, once we have this precipitate, we need a sedimentation basin. Once the softening process is over, we need recarbonation to stabilize the water. All right. Of course, this is something that has been already said. Magnesium, once magnesium is exceeding 40 milligram per liter, here at this stage where the magnesium starts to create problems of clogging, deposition, scale formation, and so on. And as we said, the practical limits goes from, for total hardness, goes from 75-80 to 120, but usually we stick to 120 milligrams per liter as total hardness of CaCO3. All right, let's discuss this problem where we are asked to go through the different softening scenarios. So let's see what we have here. We need to prepare a bar chart, okay, for hard times water. So you have the analysis, as you can see in this table. All right. You have all the constituents. So we have the carbon dioxide concentration, the calcium, the magnesium, and the alkalinity. Okay. And now it says here that we have to dose the chemicals that we need to add in order to soften the water to meet the following finished water criteria. Maximum magnesium hardness of 40 milligram per liter. It makes sense because this is the requirements. And a total hardness which goes from 80 to 120 milligram per liters, which are the practical limits approved. Okay. As we said many times, the first step to start with is to convert all the concentrations of constituents from milligram per liter as cation and anion to milligram per liter as CaCO3. Just to remind you, in order to do so, we have to take the concentrations in milligram per liter, okay, to calculate the ratio, which is the equivalent weight of CaCO3 divided by the equivalent weight of the ion. The equivalent weight of CaCO3 is fixed. It's all the time 50. And we have just to divide it by the equivalent weight of the respective anion or cation here. Okay, then we multiply the concentration in milligram per liter by the ratio that we have here in order to get the concentration as milligram per liter as CaCO3. Okay, everything is converted. Okay, as you can see, if you look to the concentration of magnesium, this is the first comment that we can have, is that the magnesium is exceeding 40 milligram per liter as CaCO3, which means that we're not fulfilling the requirements of magnesium. All right, if we add the calcium to magnesium, we have 238 plus 90. This is definitely exceeding the practical limits, which should be between 80 and 120. That's why the first decision that we can make is to go for softening. Okay, what type of softening? Let's do it with the scenarios, with the normal procedure that we had before, which is the we have to check if we need a selective calcium or we need or we need an excess lime process, which means a removal of calcium and magnesium. I will go directly to C. Okay, and let's check what we have. So we have a carbon dioxide of 12.5. Okay, so we need lime with the same concentration of carbon dioxide. This is to raise the pH. And then we need lime with the same concentration as bicarbonate, which is 198. This is to convert the bicarbonate to carbonate. Okay? And then we know, as you can see from the bar chart here, we know even if we convert the bicarbonate to carbonate, we have non-carbonate calcium hardness remaining, okay, which is here. It goes from this line up to here. Of course, now the bar chart is represented in terms of milli equivalent per liter, but we are not using this. Please, all the time, draw your bar charts with the concentration in milligram per liter SCaCO3. Anyway, so after converting all the bicarbonate, we will have non-carbonate calcium remaining. Okay, the difference between the alkalinity and the calcium, let's say we have 238, we have an alkalinity of 198, which means I will have the difference between the two. I will have 40 milligram per liter of SCaCO3 of calcium not covered by the natural alkalinity of water, which is this part. So this 40 milligram per liter of calcium not covered with the alkalinity needs an external source of carbonate. That's why we are adding here 40 soda ash. This 40 is to cover the non-carbonate calcium here. All right. What to do with the magnesium? The magnesium is 90, which is exceeding the 40, so definitely I have no choice. I have to remove it, which means selective calcium would not work out, and I have to go the excess lime process, which means a whole removal. And that's why for the magnesium, first of all, it has to be converted to MgCO3. Okay, so the concentration of magnesium is 90.6. I have to add the same quantity of soda ash here, 90.6. Once this is done, the Mg is converted to MgCO3. Okay, the problem of Mg is not solved out because MgCO3 is soluble. So I have to add lime, 90.6 of lime, in order to convert the MgCO3 to MgOH by 2, okay, which is insoluble. So now I have basically all the amounts needed of lime, all the amounts needed of soda ash. Please notice that I am just focusing on the quantities in milligram per liter SCaCO3. So first of all, the first decision that we have made here is that selective calcium removal would not work out. I need an excess lime process, okay, which means I have to remove calcium and I have to remove magnesium using this table. So the total amount or the total quantity needed of calcium is 301 milligram per liter SCaCO3, and as soda ash is 130.6 milligram per liter SCaCO3. So at this stage, if you say, okay, I will go with the excess lime process, C step A, B, and C, which is the bar chart and the table, it's enough for you to fulfill the requirements, which means to have a magnesium concentration lower than the practical solubility and to have total hardness within the practical limits. And you can stop here. Now, let's say starting from D, we want also to double check the split treatment scenario. Okay, the split treatment option. In this case, I have to calculate the X to know which fraction, okay, and what is the portion of the water that should be treated, and the other part that should be left untreated. So as I told you, Mg final usually is fixed at 40. Mg initial, it means it represents the minimum concentration of magnesium, which is 10. Okay, of course, the raw, we go back to the table, we check, okay, in the raw wastewater, the magnesium was 90.6. Okay, let's substitute this value in our equation. And finally, we will get 37.2%. What does it mean? It means that I can leave 37.2 1% untreated, and to treat, as you can see here, 1 minus this, to treat 62.8 of the water. And we have to check that after blending, we are fulfilling the requirements. Okay, what would this change in terms of quantities of lime and soda ash needed? Okay, I am treating 62.8, okay, out of the whole volume only, which means that the other part does not need to add chemicals, only for special cases, which means that um, let me go back, sorry for the flow chart, just for you to understand what I am talking about. So for this stream, I need to add chemicals because this stream has to be treated. Okay, for this stream, the first response is that I don't need to add chemicals because I should leave this stream as untreated. All right. Would this change? And we will see that we have to add some chemicals, but anyway, we um, we have to check now in the example, does this change the quantity of lime and soda ash needed? All right. So yes, here it's just a check of the total hardness, that it's not meeting the requirements from the beginning. Back again, this is something that we have done for the table. So back again, for the split treatment, it says, okay, the total hardness is not within the practical limit. So also you can go, for example, try the split treatment. Okay, let's take the part which is untreated, okay? And let's see, after blending, what would be the final hardness. Okay, we have a total hardness of raw wastewater coming from 238 of calcium, as you can see here, 90.6 of magnesium. If we take the summation of these two values, we will have a hardness of 328. So basically, in the untreated stream, the hardness would stay as 328.6 milligram per liter because this was not treated, okay? So the hardness stays the same. Okay, so I have a stream with a hardness of 328. I have another stream, which is the treated part, that should be treated to get a final concentration of 40 milligram per liter SCaCO3. Where does this come from? You would say, but you said after treatment the magnesium is 10 milligram per liter SCaCO3. Yes, so we have 10 for magnesium plus 30 for calcium. I will have a total final hardness after treatment using split is 40, which means here at this stage before blending, I should get 10. Yes, this is what we called MGI, 10 milligram per liter as magnesium, but I have 30 milligram per liter as CaCO3 as calcium solubility. The total is 40. So this stream will have at the end 40 milligram per liter as hardness. And this, which was untouched, will have the total hardness, the removal, which is in our example, the total hardness, which was unremoved, which is the 328. Now, just by applying the mixing, 62.8 of our stream having 40 has been mixed with 37.2, okay, having a hardness of 328. After mixing, what is the hardness that we can get? It is 147.4 milligram per liter SCaCO3. Okay. Is this within the practical limits? Here where we have the problem. We are fulfilling the requirements of magnesium. However, we are not fulfilling the requirements of the total hardness to be within this interval. Okay? So we need further treatment. What does it mean, further treatment? It means that we have to go through this scenario. So we have done this, okay? Final here, magnesium is fulfilling the requirements, okay? However, all right, however, the final hardness after blending is 104, it's exceeding 140, which is higher than the practical limit. So I have to go through the second stage and I need further treatment. If it was, for example, 80, you have to cut this part and you will have something similar to this scenario, only one stage, which is the split treatment. But here, in this example, when we tried the split treatment, we found out that, unfortunately, okay, the final hardness is not fulfilling the requirements. So let's go for further treatment. What to do in the further treatment? Okay, in the second stage of further treatment, in the second stage of softening, we have to deal with calcium. And why is that? As it is clarified here, because the split treatment fulfilled the requirement of magnesium. So we got a magnesium with a maximum concentration after blending of 40 milligram per liter. So why should I bother myself with a removal of magnesium? So definitely the further treatment is a selective calcium removal. So the second stage, okay, the first stage was split. The second stage is a selective calcium removal, okay? Before going through the details, let me just summarize. So either you go with option C, which means the stable, with full, which is full removal of calcium, full removal of magnesium, and this we call it X-slime process, or you say, okay, let me check the split. The split treatment, definitely we need a first stage. In the first stage, when we checked out, we found out that, okay, the magnesium is satisfying the requirements. However, the total hardness is not within the practical limits. That's why we need a second stage after the split treatment. Okay, back again. Since the split treatments fulfilled the requirement for magnesium, in the second stage, we need only to remove further calcium, okay, to lower a little bit the total hardness and to get what is needed. All right, now what to do with the further treatment? Okay, we need lime with the same concentration of carbon dioxide. We need bicarbonate, okay, back again. The whole thing here is just to remove calcium, okay, in the second stage. So basically, we have only a calcium removal here. The remaining calcium is removed in a second stage. Okay, so what you need as total lime is 210.5 of lime. Okay. Uh, addition of lime equal to carbon dioxide and HCO3 even in the second stage is necessary to achieve the control of pH. As I said, we need the lime with carbon dioxide to raise the pH. We need the lime for bicarbonate to convert it into carbonate. Okay? Now, this is done. Okay? We calculated in further treatment what should be the quantity of lime. However, here, sorry, in this, okay, we calculated, please remember, in the first stage, we calculated the hardness only. But here, with split treatment, we didn't quantify what is the amount of lime needed and what is the amount of soda ash needed in the first stage. So please, this is for the second stage, okay, which is not a split treatment. This is the first stage where we checked just that the first stage is not fulfilling the requirement. Okay, but we need certain quantities of lime and soda ash in the first stage. How can we quantify this? It's here. So I need, so I have 62.8 that should be treated. Please correct, this number is not 313, it is this value, 301.1. So this is wrong as number, okay? But since it's a PDF, please change it, take a note of that. This is 301.1. Okay, so since we don't need the whole quantity because we're not treating 100%, we're treating 62.8%, we will take 62.8% of this, okay, and okay, 62.8% of 301. Okay, and why for the untreated part, which is 37.2, we have to say 0 here, okay, normally, because we say that this is the part untreated. However, this is the quantity of lime, as you can see here, that should be added when we're not treating. But why we are taking this into consideration in the untreated part? Remember that this is the quantity of lime that should be added just to raise the pH, okay, and to convert HCO3 to CO3 minus 2. This has to be done even in the untreated part. We're not removing calcium, we're not removing magnesium, we're just adjusting the pH and converting the HCO3 minus to CO3 minus 2. So please keep in mind that this amount of lime is also needed even in the untreated part, but with a percentage of 37.2. So the total lime that should be added is 275 milligram for every liter instead of 301.1 for the whole removal, for the excess lime process. What about soda ash? Of course, the soda ash is not needed to raise the pH. That's why in the untreated, the 37.2 fraction, we don't need soda ash at all. So we put 0. But for the 62.8, as you can see, in the overall process, we need 130.6, okay? This is when we are treating the 100% of the water. But since it's not the case, we are just treating 62.8, we will take just a fraction of this quantity. And in this case, we need 82 milligram per liter soda ash to treat the water, to treat every liter instead of 130. And as you can see, even with 2 stages, one split treatment and one additional treatment, still the quantities are less than what is needed in the overall. So this example is just, let's say, a full example just to understand that we can do softening with excess lime process where we remove calcium and magnesium just by the addition of the soda ash and the lime. However, we can do it in split treatment. Please remember that in split treatment, we have to check if we need 1 stage or 2 stages. If we need 1 stage, we have to prove that we are fulfilling the requirement of calcium, the requirement of total hardness. At the same time, we have to quantify lime and soda ash. Please remember that we need lime even in the untreated, just to condition our water, just to raise the pH, to convert the HCO3 minus to CO3 minus 2. We don't need soda ash for the untreated part. So thank you very much for your attention. And now the lecture, we will stop here, and I will upload next time the lecture of Tuesday. Thank you.